Hello. Okay, so I'm going through Barbara's, um, what's it called? Subbing, no, the remove a material experiment first, and then we've got subbing fluxes down below. So Barbara did a great job. Her tests look really good and give us a lot of information about um, the changes in chemistry and how they affect the overall glaze and how it turns out. So I'm just going to kind of analyze these glazes and show you anything that stands out. So here we have our first, this is the base glaze, Hansen 2020. So we've got 0.2 to 0.8 flux ratio. We've got 0.2 moles of boron, 0.36 alumina. So everything's looking good. 9.38 silica to alumina ratio. So this is what we have to begin with. And then she had added, I don't know, what was it? Oh, yeah, it says 1% copper carbonate. And she did a slow cool. So we'll keep that in mind. So first, she removed the silica. So I'm looking at the UMF here of the original, and then I'm comparing it to the UMF of each individual glaze. So when we remove silica in the UMF, nothing except for the silica to alumina ratio. So everything stays the same. We just have less silica in the glaze. And you can see that this glaze is now running and it looks a little more transparent. I would guess that if these didn't have copper in them, this would be on the cloudy side. This would be more on the clear side of things. And the reason why it's running is, if you remember, silica melts at a very high temperature. So if we keep the fluxes the same, and say we were going from here to here, we're adding silica, which is raising the melting temperature of the glaze. So so here the glaze isn't running. Here the glaze is running. So by changing the silica, so we've got 2.28 moles of silica, 3.36. So we've added 1.1 approximately moles of silica, going from this glaze to this glaze. And that is enough to change a runny glaze into a non-runny glaze. But it also affects the transparency. So that's interesting. And I'd be curious to know whether some of this, if this has a rough surface, it's hard to tell from the test tile. If you can kind of feel the bumpiness and whether that's some blistering that's happening with the copper off-gassing, that's also something to consider. This one looks nice and smooth and very well melted, a little bit overfired, pardon. So if I liked the way that this glaze looked and I wanted to increase the temperature, what I could do is increase the alumina slightly, maybe bring the alumina up to 0.4, and then keep the silica to alumina ratio the same. And that could give possibly the same sort of look to the glaze, but with a little less running. And I'm just guessing at 0.4, so from 0.36 to 0.40. I'm just guessing that would reduce the running. It might not need that much extra alumina, but it would be worth testing. So now, test number 3, we took the original recipe and then we removed the alumina source, which was EPK. So this glaze has no EPK, no clay in it. So let's look at the UMF. The flux ratio is exactly the same because we haven't removed anything containing any fluxes. boron is exactly the same. Now we're down to 0.12 moles of alumina. So we can see on the graph, the stall chart, here is where this glaze falls way, way, way down here. So we've got, it looks like a matte glaze, probably due to the high silica to alumina ratio. So all of a sudden, because there's very little alumina, we're dividing the silica by a very small number, which gives us a very big number, 23.74. And so it looks like this glaze probably ran a little bit because it had very low alumina. It also crystallized, probably because it had low melted viscosity. And then it's cloudy, which you would expect from a very high silica to alumina ratio. So if you remember the glaze, when adding silica, you start out matte, you move into glossy, clear glossy, and then whitish glossy, and then into the underfired. I'd also be curious to feel all of these test tiles just to see what they feel like, if they're smooth or a little bit rough. Because this looks like there's some blistering bubbling. I don't know if she wrote any notes. Nope, no notes. So, but that could be due to the copper off-gassing. Okay, then here we removed the primary flux. So now the flux ratio is changing. A lot of things are changing. So we removed the feldspar. So now we have lots of calcium, a little bit of R2O, primary flux, which would contribute to having a hard time melting, but then the alumina level is also quite low. So alumina competes with the fluxes, and so we don't have a lot of primary flux to get the melting going, but then there's also not of alumina competing with it. So it looks like it melted just fine. And there's a little bit more boron because of removing one material. So the boron level went up slightly, and then 10.48. So the silica to alumina ratio also went up slightly. And it could be that this is a thicker application than this here, but these look fairly similar. And this doesn't look like it has had any trouble melting. It looks like it melted just fine, but it might not be the greatest, like it might not be well melted. It might not be the greatest as far as durability is concerned, not having that primary flux there. So it might have struggled to melt. Hard to say just by looking at pictures, but very interesting. So now we go down to we've removed the elastinite. So this is interesting. Now we've got a color change. So here in the original recipe, all of the secondary flux is calcium. And now we are down to 0.5 to 0.5 flux ratio. So, and then the flux is all still calcium, but then look, we've got 0.8 moles of alumina. So we're way, way, way up here. And that's going to have a big impact on the color of the glaze as well. So I would expect that this one is under fired, although alumina competes with the fluxes. We have extra primary flux, which is going to help the melting, but then then we have a lot of extra boron, which is going to help the melting. So we've gone from 0.21 to 0.48 moles of boron. So extra primary flux, extra boron, but then a lot of alumina. So this is just a very interesting recipe, but I believe the high alumina level and the reduced calcium level is contributing to the color change here. And then our silica to alumina ratio is still 7.8 to 9.38. So it's still fairly close, a little bit less silica. And a whole bunch of alumina. So that's very interesting. Now we've removed the boron. So, I mean, this to me looks underfired. So removing the boron brings down the primary flux, brings up the secondary flux. So now we have a flux ratio. So the boron source was Frit. Aha. So Frit 3134 not only contains boron, but it also contains fluxes and silica and not much alumina. 3134. Yeah, so no alumina, but we're removing some, definitely some primary flux. And so we have no boron. The alumina level has gone up significantly to 0.2 or 0.52. So we're over here on the stall chart. So you can see most of the recipes are down here, and then this one's kind of up here. So I would expect that this is definitely underfired at cone 6. And let's see, 8.3 silica to alumina ratio. So it's kind of we're missing information when the glaze is underfired. It might look kind of nice. It shows texture nice, but if it's underfired, if we were to fire hotter, the glaze would probably look a little more like one of these examples up here. But yeah, also very interesting. So now, let's see. We're subbing fluxes. So here is where we've substituted, it was Custer feldspar, and now we've substituted Minspar. So flux ratio is the same. Everything's the same pretty much, just a change in the source of primary flux. So we've got, for the R2O, we've got 0.17 sodium, 0.03 potassium. In the original recipe, we've got 0.14 sodium, 0.07 potassium. So it's a very small difference, and the results look pretty much the same. So replacing some potassium with a little bit of sodium isn't going to have a big impact on color. Now, I would be curious to know if these two examples, the Custer and the Minspar version, if they feel different, if one feels smoother than the other, if one, if there is some unresolved copper off gassing, whether you can kind of, whether you can notice that in the texture of the glaze. So now we have replaced Custer feldspar with Nephsi. So in doing so, we've got, so we've got more primary flux. So original recipe, I don't know how to change the order of these, but so we've got the original recipe is 0.36 alumina, 0.21, and then 0.21 to 0.79 flux ratio. So with Nephsi, we've increased the primary flux by 0.02. So we're now at 0.23 to 0.77. So a little bit of extra primary flux, a little bit of extra alumina. Proportionately, silica to alumina ratio is still around 8. So I know what I can do. I can go click and click, and I'm going to just compare. With selected, I can go calculate, and then it puts them all on the same page. But of course, I can't see the pictures as well, but I can look at the chemistry. So here's the original. So yeah, a little more alumina with the nephsi, which is interesting. But the silica has gone down, and the alumina is in proportion to the flux. So it kind of makes sense with making changes. If we're changing some of the flux, that the glass former levels are going to fluctuate a little bit. Yeah, so I would be curious to feel these just to see if one feels smoother than the other. But I would assume that they're fairly similar in kind of like substituting. It doesn't look like this one has run that much. I can only see this one side of the glaze, but it doesn't look to have run. But it looks like maybe it's a little bit better melted as far as like the possible copper off gassing is concerned. And now we've got, so I'm going to remove this one. Now we've got spodumene as the primary flux. So replacing, so we've got a little bit of extra primary flux, and then we've also got lithium. So we've replaced some of the sodium and potassium with lithium, and lithium is the most reactive, starts melting at the lowest temperature of all the primary fluxes. So that would increase the melting of the glaze, but then we've also increased the alumina slightly. So we've gone up to 0.4 moles of alumina. Boron is pretty much the same, a little bit less silica. So I'm curious to see how, yeah, it does look like this is a little more melted than the original version. But yeah, curious about that as well, to see this in real life and to feel it like, is that a drip there? Looks like a drip. And so that could be just based on the lithium melting the glaze earlier, and the glaze being in a liquid state for longer. A lot of the other levels are the same. And so I would expect it to melt at a slightly lower temperature. So now let's go back and look at, those were the primary fluxes, now the secondary fluxes. So the original recipe had wollastonite. Here we've substituted whiting gram for gram. Since wollastonite is calcium silicate and we replaced it with just calcium, then I would expect the RO to go up, which it has. So we were at 0.21 to 0.79. Now we're at 0.19 to 0.81. So a little less primary, a little more secondary flux. But then the alumina level has gone down slightly. So we were at 0.36. Now we're at 0.33. So when we reduce the primary flux and we also reduce the alumina, just by a little bit, then generally the melting stays about the same. A little tiny less boron, but not really significant. And so we haven't changed the primary flux, the secondary flux, the RO. It's still calcium. 100% calcium, so no notable color differences. So now we've substituted, in this one, we've substituted wollastonite for, we've replaced wollastonite with talc. So wollastonite is calcium silicate, talc is magnesium silicate. So now we've got 0.54 moles of magnesium and then still a little bit of calcium from the frit. And we have a bit of a color change. So we've got more of a lighter green color rather than, it has a less kind of bluish tones to it from the copper. And magnesium tends to produce not so shiny glazes. And so it looks to me like it's kind of has a duller finish, not as glossy. The alumina level pretty much stayed, it went up a little bit. The boron went up by 0.01. Silica is close to the same. Let me check. 3.36. And with talc, 3.65. So the silica went up slightly. Yeah, so this with the magnesium, it could be struggling to melt a little bit. But I mean, it looks okay to me. Hard to say. Again, it's always nice to be able to feel the test tiles. But yeah, just noting the color change here. And then strontium carb. So we're replacing calcium silicate wollastonite with pure strontium. So we're removing some silica with the wollastonite. We're removing a little bit of silica, and then we're replacing some of the calcium with strontium. So the flux ratio went up. The RO went down slightly, and that's because gram for gram, calcium is a smaller molecule and it has less molecular weight than strontium. So when you go gram for gram, calcium for strontium, you're going to have, because strontium is a bigger molecule, you're going to have less molecules in the same amount of weight. And so it makes sense that the RO would have gone down slightly doing that substitution. And then the alumina went up a little bit. The boron went up a little bit. Not a huge change in color. So, and I've noticed as well with my tests with strontium and calcium, especially the copper versions, they were very similar in color. But yeah, similar melting. There's no drip on the side here that I can see, for example, with this one. And so it's possible that this, has struggled to melt a little bit. Hard for me to know exactly, but just something to be aware of. I mean, the R2, like I was saying earlier, the R2O primary flux went up and the alumina both went up and the boron went up. So it could be just perfectly well melted as well. And then finally, dolomite, interesting results with the dolomite. So dolomite is a calcium magnesium carbonate, basically. So we're replacing wollastonite, calcium calcium silicate with calcium and magnesium. So we've got 0.5 calcium, 0.3 magnesium, which I wanted to compare with the talc. With the talc, we've got 0.54 magnesium, 0.24 calcium. So this one has a little bit extra magnesium. Wait, no, this one is calcium dominant, right? So that explains the color difference. So there is a bit of magnesium, but still calcium is the dominant RO flux. We've reduced the primary flux, but we've also reduced the alumina. And so we're down to 0.32 alumina, which, we're getting closer to that 0.3 alumina where the melted viscosity is very, very low, which can induce some crystallization. And so that's what I think is happening here with this kind of modeling effect. If we were to bring the alumina down even lower, we might get more of this streaky effect that you can see here. The boron is a little bit lower. So we've reduced the primary flux, we've reduced the boron, but then we've also reduced the alumina. And it does seem to be well melted. And then everything else looks just fine. So great work Barbara. This was really fun to go through and just see, because my test results were, a lot of them were under fired, and so they weren't very good examples. And so I thank you so much for posting this here, and I'm going to post this video to the Facebook group, and so hopefully everyone can go through it. And if anyone else has their experiments uploaded to Glaze, then I would be happy to go through your experiments as well and make a video, because I think this just kind of ties in all of the information that we've learned and what can be kind of derived from these experiments. So this is awesome. Thank you.